So before giving the microphone over to Ben, I'd like to thank the ISOM. It's an organization which is funding travel by US based people based in the US to India. His travel funds have been, travel support has come from ISOM, which is a really good thing, because we would have had difficulty finding travel for him, because our travel funds are somehow very strangely restricted only to very, very distinguished professors. I mean, so they should be older than a certain age, unfortunate. So that's unfortunate, but so thanks very much to ISOM for this. And there are exercise sheets on the web page, and Ben is also going to, he's starting some of the exercises, indicating which ones are important. The scanned copy of yesterday's notes and today's notes are already on the web page, okay? And yesterday's recording of the lecture will be up on the website today, and so today's will be up tomorrow, tomorrow's will be up on Friday, and so on. There is absolutely no excuse at all for us not to follow up on. I mean, there are exercises, there are scanned notes, and there are videos of lectures. And on top of that, Ben is available. He was sitting until 7 o'clock yesterday, helping people with exercises. I got lots of help from him. So really, I wish we make use of this wonderful opportunity. Okay, thanks again to Ben, and over to him.
All right, so today's goal is going to be to introduce the main players, the Zergel bimodules, and sort of the technology that you need to get to them. They're a categorification of the Hecke algebra, and what that means will become more clear. But it's an easy categorification. There's other categorifications, category O, Perverse, but this one's very algebraic and combinatorial. So it's very accessible. I'm going to start, though, by discussing the reflection representation and polynomials. So let's fix a Coxeter group with a choice of simple reflections. And what we're going to do for this is we're going to also choose a Cartan matrix. So many of you are probably familiar with Cartan matrices for Wall groups, although you can take a notion of a generalized Cartan matrix for any Coxeter group. So A is going to be some matrix with 2's on the diagonal, and then maybe it's an S by S matrix, and maybe in the ST spot the entry is AST. So a wide variety of things are available to use as Cartan matrices. And I'm not going to go into that. There's some bit about this on the exercise sheet, about what generality is. But for now, we can just use the symmetric Cartan matrix. And this is defined by letting AST be ATS be minus 2 cos of pi over MST. So for instance, in type A, that would be putting minus 1's on the off diagonals and 0's everywhere else, because minus 1 is minus 2 cos pi over 3. And in type B, you'd put square root of 2 somewhere, minus square root of 2. As opposed to having a minus 2 and a minus 1, the symmetric version is minus square root of 2 and minus square root of 2. Regardless, here it is. And from this matrix, we can define a representation. So let H dual be the R vector space with basis also parameterized by our simple reflections, alpha S. These things are called simple roots. And we're going to define an action of W on this vector space by the formula that S of alpha t is alpha t minus AST alpha S. So this is exactly how you would expect something to act by reflections. And these numbers are cocked up so that this is actually a representation of W. So in particular, and they're in the exercise sheet. But basically, there's going to be some representation called the reflection representation, and everything else we do will be based on this choice. So let's, and then before I give an example, one more definition. So let R be the polynomial, the coordinate ring of this, be sim H dual. Or in other words, this is just a polynomial ring on the generators alpha S. Okay, just a free polynomial ring, very boring. And of course, this is a ring. It has an action of W, since the original vector space had an action of W, and it's a graded ring with the degree of linear terms being 2. So you double the degree. This happens all the time. You should think of this maybe as the equivariant cohomology of a point. And so this is a cohomologically graded, and things have even degrees because that's how cohomology works. Cohomology of something with a complex cellular filtration is only even degree cohomology. So there's a reason for this grading, but it's not so important at the moment. And then finally, for a subset of the simple reflections, there's a corresponding parabolic subgroup, which is the subgroup generated by these simple reflections inside W. This is also itself a Coxeter group. And we're going to let Ri just denote the invariants under this parabolic subgroup. Right, this is the F such that SF equals F for all S in I. Okay. So we've got this polynomial ring as well as a bunch of subrings given by invariants. So let's give some examples. And the best examples are, of course, the symmetric group. This is supposed to act on this ring R, which in this case you can think of as just polynomials in n variables, where Sn is acting to permute the variables. Now, if you're careful about it, this is not quite the definition that I gave here. There's only n minus 1 simple reflections, and so this is an n minus 1 dimensional vector space. Really what's happening is that you're doing this and you're modding out by the sum of the xi's is 0. But you can really ignore this. As I said, you can choose a representation, basically, and work with this. So it's OK to ignore this. If you want to, it doesn't make a difference. And there's supposed to be some simple roots inside here. So the ith simple root is xi minus xi plus 1. And then you can check that this obeys those rules. Now, suppose that you have a parabolic subgroup. Parabolic subgroups look like this. You take a partition of n, or a composition of n, and you have something like S3 cross S1 cross S2 cross dot inside Sn. And so Ri, then, is going to be polynomials that are symmetric in the first 3 variables, and then the next variable, and then so forth. So this is actually, it's known that this has that this is itself a polynomial ring. Okay? That this is generated by elementary symmetric polynomials. So instead of having the generators x1, x2, and x3, we can replace it with the generators x1 plus x2 plus x3. That's the first elementary symmetric polynomial. x1, x2 plus x1, x3 plus x2, x3. That's the second one. x1, x2, x3. And then we can move on to the next part. Well, that's just x4 all by itself. And then the next part, x5 plus x6, and x5, x6, etc. Okay? But the point is that these terms are all algebraically independent. There's no relations between these things. So this is itself just another polynomial ring, except it's generated in different degrees. Okay, so this is a theorem, a famous theorem of Chevalier. And it's something very, very special about Coxeter groups. It's really unique to Coxeter groups that this happens. Theorem of Chevalier that, I guess a little quick definition, if Wi is finite, we just say that I is finitary or finitary. It's just a stupid little fast way of saying things. So if I is finitary, then Ri is itself a polynomial ring. A polynomial ring of the same transcendence degree as the original polynomial ring. There are n generators in R, there's n generators in Ri. Of same transcendence degree. So it's generated by some homogeneous polynomials in various degrees. Yes, but this is only when W could be infinite, yes. But Wi, it has to be finite. That's exactly right. The actual generators that you choose for your subring vary, right? You don't have to choose the elementary symmetric polynomials. You could choose complete symmetric polynomials, and so forth. The degrees of the generators are determined by Wi. So this is, in fact, there's many nice properties of these degrees. They add up to the number of roots, and the product is the size of Wi. So there's all these sort of beautiful things. You can find these in Humphreys, and some of it's in the exercise. So the point is that the rings Ri are nice rings. They're nice, happy things. Okay? This is actually an if and only if. All right? If you have a group acting on a vector space, and you look at the ring of polynomials, and you look at the invariants, this is almost never a polynomial ring. It usually has some sort of weird algebraic dependencies.
A little more, not just to reflections, pseudo reflections.
Say that again?
No, not just reflections.
Yes.
Pseudo reflections are also.
Ah, yes, yeah, exactly. Complex reflections. That's right. That's slightly more general. But so this is all nice and good. But what I'm going to now introduce is a souped-up version of this. Okay, a slightly better version of this. And so the actual theorem, it's really this in another language, but with more property, is that this extension of rings is a Frobenius extension. So what does that mean? And also, so is, if you have two various such invariant subrings, if I is contained in J, then everything that's invariant in J is also invariant in I, so you have this inclusion of subrings. And if both of these are finitary, then both of these are polynomial rings with the same transcendence degree, and in fact, this thing is also a Frobenius extension. That's just what I was going to say. So what is a Frobenius extension? So Frobenius extensions are actually, they may be familiar from sort of finite group theory. So we'll see if it rings a bell. So, well, let's work with commutative rings. So a commutative ring extension A inside B is Frobenius extension if equipped, so it's a bit of extra data, if equipped with some trace map from B back to A. So this thing has to be A bilinear. well, I mean, it's a commutative ring, so A acts the same on the left and right, so it's just A linear. Such that B is free as an A module. Yeah, A linear, yeah. I don't know why I wrote bilinear. A linear, it's the same thing, it's commutative. So B is free as an A module. So you can choose a basis, but in fact we can choose dual bases. Dual bases. So you can choose one basis BI and another basis BI star, such that if you apply this delta to BI times BJ star, you get delta IJ. Okay, so there's this, given this trace, you end up with a pairing. Given two elements of B, you multiply them together and apply this, and you get an element A. And the claim is that this pairing is perfect. Non-degenerate, essentially. So the point is that, you know, if A were just a field, this would be really something like a trace map. So if A is a field and B is matrices, you can think that this is the trace. But yeah, this is sort of a more general notion. And I suppose when A and B are graded rings, then you want the dual bases, you want delta to be a homogeneous map of some degree. And the dual bases to also be homogeneous. So that's a notion of a graded Frobenius extension. And if the degree of delta is minus 2L, then we say it's a graded Frobenius extension of degree L. So why did I double it? You'll see soon. OK, so this is just a weird abstract definition. But what's the utility of such a thing? So the point of Frobenius extensions is Frobenius reciprocity. So this is something you may remember. Here's an example of a non-commutative Frobenius extension. Okay, that if H contained in G are finite groups, then CH contained in CG is a Frobenius extension. Okay? And what made this special is that you have induction and restriction between H modules and G modules, and that these are not just adjoint in one direction, they're adjoint in both directions. That was what Frobenius reciprocity said. So this is the general feature that this is supposed to mimic. Okay? So let's go into this. So the bimodule B as a left B module and a right A module. Okay? The map backwards is some kind of H averaging. What is it? I don't remember. It's actually been a while. I don't remember.
No, special case, reciprocity is going out.
Yes. Yeah, well, exactly. I don't remember. OK, so this bimodule, B as an A right module and a B module, you can tensor an A module with this thing to get a B module. And this gives you a functor from A modules to B modules. So whenever I think of a bimodule, I'm always thinking of it as a functor. Okay? So this thing is induction. Okay, given an A module, if you induce it to a B module, that's another way of saying that is you tensor over A with this bimodule. So this is called induction. Meanwhile, if you view it as a right B module and a left A module, you can tensor over B and take a B module and get an A module. But taking a B module and tensoring over B with B is doing nothing to it. You're just viewing it as a left A module. So this is restriction. Okay? And for any ring extension, not just a Frobenius extension, induction is left adjoint to restriction. Okay? Which is to say that Hom from the induction of M to N, so I guess M is an A module and N is a B module, and this is a map of B modules, is naturally isomorphic to Hom from M to the restriction of N. Okay? And how do you determine these isomorphisms? How do you determine this isomorphism? There's something called the unit and co-unit of a junction. Is this stuff familiar to many people, or is this totally new? No one? Volunteering. OK. So it's determined. So a junction is a structure. It's not just a property. It's determined by the unit and co-unit of a junction. So if you've never seen this before, it's maybe worth seeing. Let me go back here to this little thing here. If you plug in a special case, okay, so maybe M, which is an A module, is the restriction of another module. Okay, so maybe this is the restriction of N. Okay, so then you get Hom B from the induction of the restriction of N to N is isomorphic to Hom from the restriction of N to the restriction of N. Now this thing right here has the identity map, so that corresponds to some special map here. Okay, and moreover, this special map is very functorial in N, which means that what you actually have is not just a map from ind res N to N, but you have a natural transformation of functors from ind res to the identity. Okay, this is either the unit or the co-unit, I forget which. Okay, so you have a natural transformation to the identity of B modules. Okay, well, what is ind res? Okay, we start with we start with a B module, we tensor with B as an A module, and then we compose this. So we compose functors with B like this. So let me just delete this. Okay, this is B tensor over AB, tensoring with this bimodule, and tensoring with B itself as a B bimodule is the identity functor that does nothing. So there's some sort of map of B bimodules from here to here. Okay? What map is this? It's multiplication. That's exactly right. Okay? I mean, there's a very canonical thing you can do. You've got two elements of B, you multiply them, that's clearly alinear. Okay? And this is true, again, for any ring. All right? There's no Frobenius anything. You can always define multiplication. So similarly, you also have a natural transformation from the identity of A modules to res of ind. And so what would this be? If you work it out, this is a map from A as an A bimodule to B as an A bimodule. And what is this map inclusion? So this is something you can do for, and so you have the pair of these things, and they satisfy some relations with respect to each other, which we'll look at soon. Well, if you're supposed to have an adjunction in the other direction, so for Frobenius extensions, you also have that restriction is left adjoint to induction. Okay, that means that you have maps. You know, you've exactly flipped the role of res and in, so you have maps in the other direction.
So what you've written by the functor is actually tensored by this function.
Yes.
So there is an argument tensor dot.
Yes, exactly. There's a map from bimodules to there's a map from bim to cat, which takes a bimodule and sends it to the functor of tensoring with that. Because natural transformations between functors of tensoring with a bimodule is the same thing as bimodule map. This is just a sort of a standard algebra fact. Okay. So we have all the maps in the other direction. So we have some map of A modules, A bimodules from B to A. This is exactly this delta, which is in the structure of the Frobenius extension. And there's also a map from B as a B bimodule to B tensor over A, B. And this is a weirder thing to describe. It's called delta, the co-multiplication. And delta of 1 in here is this sum over dual bases, this sort of Casimir element-like thing. Okay? So the point is that this guy is the unique element of B tensor over AB for which left multiplication and right multiplication are the same. Okay? All right. So left multiplication and right multiplication by an element of A are clearly the same because that's the notion of a tensor product. But left multiplication and right multiplication by an arbitrary element of B will not be the same. However, on this particular element they are. Okay? Clearly they're the same on this module, so its image must also. Okay. So this is, and this element also, while defined using a dual basis, does not depend on the choice. Choice of dual bases. So that's why this delta was part of the structure of a Frobenius extension, whereas the existence of dual bases was just a property. You don't actually need to choose dual bases. Okay? So that is why Frobenius extensions, so you can check that these satisfy all the properties that need to be satisfied to be adjunction maps. With the grading, how do you just handle things, right? It's no longer true that induction and restriction are actually adjoint to each other on the nose. So actually, as always for anything, induction and restriction are adjoint to each other in this direction, but restriction is actually adjoint to the shift of induction by the grading shift 2L. So this is the functor which takes a module and shifts its grading. Okay. And so because of this, you don't quite have biadjunction on the nose, but there's sort of a nice way of just rescaling the gradings here in a nice sort of homogeneous way. So you have these 4 maps, 1, 2, 3, 4. But what you do is you put a grading shift on this object by L. And so everywhere this object appears shifted by L, and everywhere sort of B as an A bimodule appears also shifted by L. Okay, so now you have these 4 maps defined in exactly the same way, but these are homogeneous maps of degree plus L, minus L, and minus L. Okay, all right. All right, so this multiplication is a homogeneous map of degree 0, normally. Okay, so then after you put the grading shift in here, it becomes degree plus L. Okay. Similarly, this thing is normally a homogeneous map of degree minus 2L. After the grading shift, it becomes just minus L. Okay. So this is the grading convention you use. It's basically saying that induction and restriction with the shift are adjoint to each other. So if you put the shift here instead, then you can get something similar on both sides. I mean, there's some sort of general notion that geometry produces tons of Frobenius extensions. Whenever you have a proper map between algebraic varieties, you're going to end up with the push forward and the pullback being biadjoint up to a shift. And the shift being the dimension difference between the two spaces. This is why this sort of thing appears. And this renormalization is very common in geometry as well. So again, there's reasons for this kind of mumbo jumbo, but for now it's just something you can accept. All right, so let's do it in examples. I said that Ri is supposed to be a Frobenius, Ri inside R is a Frobenius extension. So let's do the first example of Rs inside R. Okay, so choose a simple reflection, look at the invariants. Okay, what is this subring? It's a polynomial ring. Okay, well, so what is this ring? Okay, so claim. Rs is the polynomial ring generated by a bunch of linear terms. Well, which linear terms? Anything that's in our representation that's invariant will give an invariant polynomial. So alpha t plus cos pi over mst alpha s. So for t not equal to s. So what is this stuff, right? You've got alpha s here. You got alpha t here. The action of s on alpha t sends that to alpha t plus 2 cos pi over mst alpha s. So what you do to act by s is you reflect over this line, and that adds to alpha t twice this distance. And if you use trigonometry, this distance right here is cos pi over mst. Well, if you only added once that distance instead of twice, you'd end up with something on the perpendicular line. This thing is invariant. It's also the average of these two things. So it's invariant. And then alpha s itself is not invariant, but alpha s squared is invariant. Alpha s goes to minus alpha s, so alpha s squared is invariant. Yes. So we chose, yeah, exactly. So it's a polynomial ring generated by a bunch of linear terms and one quadratic term, which is what you'd expect. Because we're taking invariance under Z mod 2Z. Okay. So our definition then is that we'll define ds from R to Rs by the following formula. ds of f is f minus sf divided by alpha s. Okay. So a priori, this thing doesn't look like a polynomial because we divided by something, but it turns out that the numerator divides, the denominator divides the numerator. This is a genuine polynomial. This operator is called the Demazure operator. And you can check that the degree of this operator is -2, right? We don't change the degree in the numerator, but then we divide by something of degree 2. Okay. The reason that it's a genuine polynomial is that the numerator is anti-invariant. Maybe R minus s can denote those f for which sf is minus f. Anti-invariance. And it turns out that this is a free module over invariance. Generated by alpha s. So that's why the numerator divides the denominator. Okay? So now you have to check a whole bunch of things. This is, in fact, a Frobenius extension. Well, all you need to check is that it's Rs linear and that it has dual bases. Okay? Well, maybe I'll just write facts. These are exercises. Okay? So ds is Rs linear. ds kills Rs. So if you have something that's already symmetric, then f minus sf is clearly 0. We can choose dual bases like so. 1 and alpha s over 2 and alpha s over 2 and 1 are dual bases. All right, why is that the case? It's a very quick calculation to see that ds of alpha s is 2. So ds of alpha s over 2 is 1. So this pairs to 1, and this pairs to 1. And then this is symmetric, and the product of these two is symmetric. So therefore, by this property, the bases are orthogonal. These parts are orthogonal. Genuinely dual. Maybe I should note that ds of alpha t is exactly ast, this entry of the Cartesian. Then we also have the twisted Leibniz rule. Which says that ds of fg is, so normally when you take a derivation, you have some sum with two terms, and you'd have f dsg here, except actually you have to twist it. Okay, here's the twisted Leibniz rule. And then finally, you have the braid relations. So if you choose two different ds and dt, okay, then actually ds, dt, ds, dt, etc., is equal to dt, ds, dt, ds as operators. Okay. And this is lovely because if you take a polynomial and you apply ds, you get something that's invariant under S. Then you apply dt, and you get something that's invariant under t, but no longer invariant under S. Then you apply ds again, you get something invariant under S again, but not invariant under t. Okay? But because this is equal to that, then the result of applying the whole thing is both invariant under S and invariant under t, because the last thing you did was apply ds, whereas the last thing you did was apply dt. So these are operators, these are maps from R to things which are invariant under both S and t. Okay, and of course, this only makes sense when MST is finite. So actually, this will give us our Frobenius extension for this. This is the Frobenius trace map for this ring extension. And from this, in fact, you can then build the Frobenius extension for all. All right. So I want to give you sort of one of the consequences of this. So if we take R and we view it as an RS bimodule, so as a vector space, you can split any function into its invariant part and its anti-invariant part using the usual methods. Okay? And well, actually, this is an isomorphism actually as RS modules, or bimodules. And as RS modules, this is RS plus RS shifted by -2. Again, this is a free module of rank 1 generated by 1. This is a free module of rank 1 generated by alpha S, which is in degree 2. So you shift it up. And how do you write this decomposition? Given an element f here, you should be able to get a pair of symmetric polynomials, g and h. In other words, f is supposed to be equal to, it's actually going to be the case that f is g plus h times alpha s. Actually, alpha s over 2 is a better generator. Let's use alpha s over 2. Okay? And to get these things, you let h be ds of f, and g be ds of f times alpha s over 2. And you can check that this gives you, so I guess the map going backwards is given by this. The map going forwards is given by these two formulas. You can check that this gives you the isomers. So lots of fun little exercises.
You say anything about entire square?
Say that again?
Entire square, did you say anything?
Yes, I have not yet said that, but it's quite clear. Thank you. Delta S squared is 0. Thank you. I forgot that because first delta S gets you to RS and the second one kills you. Thank you. All right, so maybe the thing that follows from the braid relations is that, so you can define D of an expression to just be D of S1, D of S2, et cetera, as usual. And the point is that this is 0 unless W is a reduced expression, because ds squared is 0. And by the braid relation, if reduced, it's independent of choice of reduced expression. So we can just write D of W because of the braid relation. And so the Frobenius map from R to Ri is actually D of the longest element of this finite parabolic subgroup, the highest in the broad order. All right. So just for the sake of those of you who are geometers, I wanted to mention one place you've kind of seen this before.
The Frobenius map itself is the delta of longest integral.
Yes. It is the Frobenius map. The Frobenius structure map. So I just want to give you a little sort of example where you've seen something basically like this before. So when W is a Weil group, then if we take R and we divide by all the invariants of positive degree, this is called the co-invariant ring. It really shouldn't be, because they're not co-invariants. They're modding out by invariants, but whatever. But this is also the same thing as the cohomology ring of the flag variety of G mod B. So this is a finite dimensional ring. And it has a trace map from C to R, which is integration, right? It's a proper integrate against the top class. Okay? So this is a general thing you can do with the cohomology ring of a smooth projective variety. And the dual bases are given by Schubert calculus. The Schubert polynomials and the dual Schubert polynomials. Okay? And these dual bases are actually root system theoretic. Okay? The top class, this thing that you're integrating against, is the product of all the positive roots. Okay? And then to get other elements of these dual bases, you take this product of all the roots and you apply Demazure operators to it. Let's call this, I don't know, L or something. Apply it to L. So these things give you one of the two bases. That's the Schubert basis. So this thing right here is the Schubert basis. It gives you, if you range over all elements of W, this gives you a basis. Yeah.
Okay, and this is product of all?
This is the product of all the positive roots. So I told you what the simple roots in R were. The other positive roots. This is for a Weil group, right? This is.
W will not play a role. Only the positive roots which are concerned with W will not play a role. All positive roots.
Yes. Yeah. Well, yeah. Right. What we're doing basically is an example for all of W. Is what we're thinking here. So this is our Schubert basis, and the dual basis is defined similarly. So this is something that's maybe familiar from geometry. Okay? What we're doing is a relative version of this. Instead of modding out by invariance, we're interested in the extension of RW inside R. So what we're doing is different. Okay, I'll put it here because I don't want to use a space. So we're interested in the relative version. RW inside R. Okay? So actually, geometrically, this is the B equivariant cohomology of a point, and this is the G equivariant cohomology of a point. So instead of doing G mod B, we do G over B. So the point is that the Schubert basis no longer gives dual bases. Okay? Schubert basis is not good enough. Okay? So over here, if you took D of the Schubert basis associated to W and then the dual Schubert basis associated to V, you'd get delta WV. That's what you're supposed to get. But that's because we've modded out by polynomials of positive degree. The Schubert basis still makes sense here. Okay? And it does give you a basis. But now, if you apply D to the Schubert basis and the dual Schubert basis, you get delta WV plus some symmetric polynomial of positive degree. Okay? Which is not necessarily 0. So these aren't dual bases. They can just be extended to dual bases. The combinatorics is much more difficult in this relative version. No one's really studied it.
Length of B and W, there's no.
Yeah, these are two elements of the wall group.
No length condition. Any two elements.
Any two elements, yeah. Okay. So this is what a dual basis is supposed to satisfy. And over here, the Schubert bases are dual bases. Over here, the Schubert bases are not dual bases. They're dual modulo higher terms. And you have to do some upper triangular argument to find a dual basis. One exists, but the combinatorics of this is very difficult. And this is a totally open problem, is to find a root theoretic description of dual bases for this Frobenius extension. So this is, I would love for someone to do this. I don't know. It's sort of funny to me that everyone studied Schubert calculus, but not relative Schubert calculus. All right. So. Are there any other, sorry. Are there other dual, I mean, there's all sorts of dual bases, right? But are there other known sort of commonly used dual bases? Probably. I can't really think of that many. Yes, there are, right? Yeah, but I'm not an expert on this. I'm not a Schubert calculus person. So yeah, so my open problem for you is find a root theoretic description of dual bases for all these Frobenius extensions, Ri inside Rj, for any Coxeter group. Okay. So should we take a break now, or should? Because I'm about to go to chapter 2. Or at least write the title. Okay. Zergel bimodules. There we go. Time to take a break.
So, back to the problem. So you want
Yep.
Ri sitting inside Rj, and so that is what is the Frobenius extension. And
Yes.
you want the dual basis explained just in terms of I and J.
Yes. Exactly.
See, here that I was thinking whether we can replace instead of L by W, only those positive roots which are made negative by W will play any role.
Only those positive, right, exactly.
Context,
So I mean, this is an important thing when you're working with R and Ri, of course, yes. And when you're working with Ri and Rj, you look at the roots that are in one that aren't in the other, and these will be part of what you're doing, right? This is certainly going to give you one of your two bases, maybe. But to find the dual basis to it is combinatorially seems to be difficult. Yeah, I think I put down as a very mean exercise to do this for dihedral groups. I mean, I've done this myself for dihedral groups. It's just a real pain in the ass.
So the answer is no for that.
Yes, but it's not a good answer. I don't have a satisfying answer. I mean, I found it explicitly, but that doesn't mean that it's anything intuitive. All right. So, Zergel bimodules. So, I'm going to start by defining my favorite bimodule. Here it is. BS is going to be R tensored over RS with R viewed as an R bimodule. Okay, so what is this? This is induction. So restriction followed by induction. Oh, sorry. With a grading shift by 1. Okay, so this is induction followed by restriction with a grading shift, and as a result, this is actually self bi-adjoint. That is, it's adjoint to itself on both the right and the left. Right, if you're adjoint to yourself on the left, you're also adjoint to yourself on the right. Okay, so this thing is self-adjoint, but how should you think about it? I visualize as a wall, or maybe a border. So here's this border labeled by S, and there's a gate there, and the security guards only let, so you've got a polynomial on one side, and a polynomial on the other side. I'll write F1 and F2. And the security guards only let S invariant polynomials through. Okay? So if you want to get through the wall, you have to get to that side. So you have sums of things of this form. That's what this tensor product is. So it's a semi-porous wall. And so, for instance, if we can write F as G plus H alpha S over 2, where G and H are symmetric. So remember, we can always do this, split F into its invariant and anti-invariant parts. Then, for instance, F tensor 1, this is my notation for F tensor 1, is just equal to, or maybe I won't even write this, F tensor 1 is equal to, well, the G slides across, so you can do 1 tensor G, plus the H slides across, leaving behind the alpha S over 2. So you've got relations of this form. Okay? And because of this, any element of this bimodule can be written with a polynomial on the right and 1 on the left, or a polynomial on the right and alpha S over 2 on the left. Meaning that this thing is free. It's actually free as a right R module with this basis. So free as a right R module with basis 1 tensor 1 and alpha S tensor 1. Okay, it's also free as the left module. Okay, but it's not free as a bimodule, of course. So, so this, the fact that these span it is I've demonstrated. The fact that it's free, this is maybe a good exercise. So this is actually quite straightforward. So this is not the most natural basis I could have chosen. Like, there's nothing special about this element, alpha S tensor 1. But there is an element for which something is special. CS is going to be this coproduct element, this sum over dual bases. So alpha S over 2 tensor 1 plus 1 tensor alpha S over 2. And this is the magic element for which F times CS is CS times F. That is, left multiplication and right multiplication are the same for all polynomials. So this is a good exercise. A little less abstract than showing it in general. You can do this very explicitly for CS. Okay, so I choose the basis. So BS has a basis given by 1 tensor 1 And I like to write CS as a right module. It's also actually the same basis now works as a right or left module. All right. I put it in the middle because it actually has things on both sides. So this is a little bit of diagrammatic notation. It's not the diagrams that we'll be talking about later, but it makes my life easier to stop drawing tensor products and just draw walls. It's easier to think about. Okay, so a Bot-Samelson module, or a Bot-Samelson bimodule. It's not Samuelson, it's actually just Samelson. Will be something that's given by an expression, not necessarily reduced. And it's BS1 tensor over R, BS2 tensor over R, dot, dot, dot. Right, it's something in the monoidal category generated by BS. So, more explicitly, this is R tensor over RS, RS1 to R tensor over RS2, tensor over RSD, R, with a shift by D. So you think of this as having D different walls. So you've got D plus 1 slots where you can put polynomials. And each wall has a different security officer that only lets certain polynomials through. Okay? And this shift, just so you remember the conventions, says that the lowest. So this has a canonical lowest degree element, which I'm going to be writing as C-bot, canonical bottom, which is 1 tensor 1 tensor 1 tensor 1. This is obviously the element of lowest degree. Spans this one-dimensional space, and this is in degree minus D. That's what this grading convention is. Okay. So, there's all sorts of places you can put polynomials, which means that there's actually D plus 1 distinct R actions on this bimodule. But we only care about the left one and the right one. Okay? That is, when we're discussing morphisms between these things, the only thing that they have to preserve is being left linear and right linear. They don't have to be middle linear. Okay. So, exercise, since BS has this basis as a right R module, in the future, I am never going to write tensor over R again. I'm going to write this as BS1, BS2, BSD. For these kind of things, because it's tensoring over some subring, I'll write the tensor product. But for this, I won't. And the exercise is that BSW has a basis given by these things C sub epsilon. So epsilon will be a sequence of zeros and ones, like a subsequence. Okay? And C sub epsilon will be CS1 to the epsilon 1, CS2 to the epsilon 2, CSD to the epsilon D. By which I mean, you either put 1 tensor 1 in that slot or you put CS in that slot. Okay? So something like CS2, CS3, something like that. Okay, so this will be a basis as a right or a left module. Okay, so figure out what these elements even are. Okay, great. So let's start to examine these Bot-Samelson bimodules and what they are good for. And the first thing that we'll look at will be a consequence of this consequence. So let's look at BS tensor BS. So it's examination time. Let's start by looking at BS, BS. Okay? So this is R tensor over RS, R tensor over RS, R. Shift by 2. Now, we care about this thing as a bimodule. Okay? So this middle R is only affected by the left action of RS and the right action of RS. That's the only thing the security officers allow in. And so anything we can do to R as an RS bimodule, we can do to this whole thing as an R bimodule. So the fact that R as an RS bimodule splits into 2 copies of RS says that we can do the same thing here. So this is isomorphic now as an R bimodule to R tensor over RS, RS plus RS minus 2, tensor over RS, R shifted by 2. Okay, just plugging that decomposition into the middle. Now, tensoring over RS with RS does nothing. So if you just work out what this is R tensor over RS, R shifted by 2, plus R tensor over RS, R shifted by 0. Which was exactly BS plus shifted by 1 plus BS shifted by minus 1. All right. So going through this long process, you can do that, but a good exercise is to write down directly the maps from here to here and there. It's very similar. I wrote down directly this decomposition, the 2 maps in either direction. You should do the same thing here. As you got a triple of polynomials, things between the 2 walls, sent to various doubles of polynomials. So write this down. Okay. So does this look familiar? It looks familiar to those who know what the punchline is. Here's the punchline. Remember from the Hecke algebra, in the Hecke algebra from yesterday, there were these elements h underscore s. And what happened h underscore s times h underscore s was h underscore s times v plus h underscore s times v inverse. Okay? So if v is a grading shift, and h underscore s is replaced by bs, plus is replaced by direct sum, times is replaced by tensor product, then this equation becomes this equation. Okay, this is the categorification of this one. So in general, this is what's going to happen. Bot-Samelson bimodules are going to categorify the Hecke algebra. Okay, and bs is going to go to h underscore s. So before we look at the other relations in the Hecke algebra, let's just do some more examination. Some more examples. Well, let's look at BS, BT. Okay, we've got 2 walls. I should use different colors now, since we have different colors. Okay, we've got our red S wall and our green T wall. And we've got 3 polynomials. Something like this. Okay, so what's good about this is that the polynomial in the middle can be split out. Okay? Well, you know, it's not necessarily invariant in S, but you can split it into its S invariant part and its S anti-invariant part and slide one out. Oh, the S anti-invariant part is stuck here, but you know, the alpha S is stuck here. Alpha S is not symmetric under T. But, you know, then you can slide something else out. You know, and then slide something else out. In fact, the point is that R is generated by RS and RT. Right, this is all but one linear term. This is all but one linear term. They don't agree. So you have all the linear terms. Which is to say that we can rewrite F2 as some sort of polynomial in S symmetric parts and T symmetric parts. We can slide the S ones to the left and the T ones to the right. Okay? So we can get everything out of the middle. And so as a bimodule, it's generated by 1 tensor 1. can remove F2 from middle. So as a bimodule, it's generated by C-bot, 1 tensor, 1 tensor, 1. So in particular, we have this element C-bot, 1 tensor, 1 tensor, 1. Okay? And this guy gives us a map. So we have a surjective map. Okay? So what can you do to 1 tensor, 1 tensor, 1? Well, you can multiply on the left by a polynomial and multiply by a right on a polynomial. Anything symmetric in both S and T can slide all the way across. Okay? So certainly, there's a map from this guy to this guy, right, sending F tensor G to F G. The one in the middle. Okay? Certainly, this map is well defined. And we've just said that it's surjective. Okay? But it will not necessarily have an inverse. Okay? So the big question is, does there exist an inverse? Question mark, question mark. Right, you know, in other words, is there a canonical way to slide F2 out? Okay? You know, obviously, if we slide F2 out in some way, and another way is related into it by sliding something symmetric all the way from right to left, those might as well be the same way to slide it out. But maybe there's multiple ways of sliding F2 out that aren't actually related in that sense. This is another sort of rough rephrasing of what it means for there to be an inverse. And the answer is when MST is 2, yes. This is an exercise on your sheet. Else, no. Okay? So, okay, that's it. So when MST is 2, we see that this is an isomorphism. Now maybe I can put this as number 3. MST is 2. So we have that R tensor over RST R is isomorphic to BS BT. But this guy, if you switch S and T, you know, the rules of S and T are entirely the same here. So it's also isomorphic to TS. Okay? So in particular, BSBT is isomorphic to BTBS. And that categorifies the relation that HSHT was equal to HTHS. That's the braid relation when M is 2. Okay, the modified version of the braid relation for the cosmos, which happens to be the same when M is 2. When M is not 2, you need to be more subtle. Okay. I'll state something. So I'll state this, but not prove it yet. In fact, BS BT BS BT to the dot alternating of length M has as a summand R tensor over RST R. Okay? So when M is 2, the entire thing is this. But when M is, but for an M higher than 2, this is just the summand. So we'll show this. Okay, cool. So next we have 4, I think. So let's do the MST is 3 case and actually investigate what's going on. So we have BS, BT, BS. All right, which means that we have something that looks like this. We can put 4 polynomials in. Okay? And now we can say that we can slide things out. So by the same exact argument, we can get rid of F2. All right, we can make split the F2 into some F3 and F1. Okay? And then we can take F3 and symmetrize it, anti-symmetrize it to get most of it all the way out across the red line. But what's left behind is, say, an alpha S. Well, we could then try to get this back across there and make a similar argument, but in fact, there's an alpha s that's going to be stuck between these two red walls, and alpha s can never get across red walls. The security guards won't let them through. Okay? So, I mean, why put alpha s here? Maybe it's better to put something else. This thing element's not canonical, but there's a canonical element. Regardless, some linear term can get stuck there. Okay? So my claim, yes. I did lie. I don't know if this is your question. Sorry, that is important. When m is infinity, Rs and Rt are actually the same. Okay, there's some degeneracy in the action of S and the action of T are actually the same. So, sorry, they're not the same action, but when m is infinity, both of these things are alpha s plus alpha t. The same linear term generates them both. They're different rings, but they have the same linear term, and so they won't together generate terms. So, sorry. So what was your question?
Okay,
Yeah.
So that whether so there is definitely a map there the moment you have more than ESPT.
Yes, exactly. There's certainly a map from here to anything. It doesn't have to be m, right? It could be lower things.
Yeah,
but
more than
right.
That's
That's right. But in order for this map to have a left inverse, right, in order for it to be an inclusion and therefore to be a projection, this must be, you have to have the right number.
For example, MST is 4.
Yeah.
And we have only 3 STS.
Yes.
Then there is no.
Yeah, there's a map here, but no map back. No map of degree 0 back. I should have said, this isn't, I should have put the 2 here in order for the degrees to match up. And then in order for the degrees to match up here, I should put an m. Sorry about that. All right, so back to this examination. So the claim is that the SBTBS is generated as an R bimodule by C bot, right, which is just 1 tensor, 1 tensor, 1 tensor, 1, and by some linear term stuck in the middle. What linear term are we going to put there? Why not CT? That's the most canonical thing I can think of. Okay? And the action of R won't actually, it's actually, this is splitting as an R bimodule. These two things are disjoint. Okay? So this thing, the things that you can reach, clearly, as we've discussed, there's a map, a surjective map from R tensor over RST, R shifted by 3, to this guy, sending 1 tensor 1 to 1, 1, 1, 1. I need to get used to the head shaking thing. I can't figure out whether you're shaking your heads yes or no here. Now, what happens here? Okay? So we're allowed to put polynomials on the right and left. Okay? And what can slide across? So if it's symmetric in both S and T, it certainly slides. But what else? If it's just symmetric in S, it slides across the red wall, and then it goes right through there. This guy's a hole in the wall. All right? Remember that multiplication on the left and the right on this guy is the same. That's why I drew it this way. This is a hole. This guy is, you bribe the security officer, you get right through. Anything gets through. Okay? This guy's not very selective. So if you're symmetric under S, you get through the red wall, you get through this for free, and then you get through the other red wall. So actually, this has a map from R tensor over you know, because this thing is in degree -1. It's degree -3, but then you added something of degree 2, so this degree is -1. This is BS. Okay? So you take two polynomials on either side of a red wall, and you just put them here with a CT in the middle. And this is a bimodule map. Okay? And so it turns out that this actually gives you a splitting. Okay? So the claim, and this is, I think, part of the exercise, but finding the inverse maps is a pain in the ass. It's really, really annoying. But this works. Is that BTBS? Yes, exactly. Is isomorphic to BS plus this thing. So actually, let me introduce some notation. Just for fun, I'm going to call this B sub ST. Okay? I'll give a slightly more general definition in a sec. But so it's this. Okay, so this is when m is 3. Don't forget that. Okay, and what does this categorify? This categorifies HS, HT, HS is equal to HS plus HSTS. The longest element of that dihedral parabolic system.
Would that conflict with your other notation B sub?
Yeah, so actually this is going to be B. So what I really meant by this is B sub ST as a set. Just like this should really be ST as a set. But this actually is also going to be B sub STS. There will be a notation for this as well. Okay, so I'll give the notation in a sec. Let's just finish this. Okay, and then you can do something else when m is 4 and something else when m is 5, and it gets progressively more and more complicated, which is why we need a better solution, right? Finding the inverse maps here is already really annoying, as you'll see on your exercise sheet, if you decide to do that exercise. Or as you know, the answer is in a paper, so you can also look it up just to see how annoying it is. But regardless, one has the theorem of Zergel. He proved using sort of different methods that there's a map from the Hecke algebra to the Grothendieck group of R bimodules. Okay? It sends HS to the class of BS. So remember, the Grothendieck group of a graded monoidal category is a Z V V inverse algebra. All right, V is grading shift. Multiplication is take tensor product.
BS isomorphic to BT?
Nope. No.
BS and BT are not isomorphic.
That's correct.
In the case STS is 3.
Yeah.
Even there it's not, they are not isomorphic.
Yes, definitely not. Absolutely not. Now, on one side, you have different security officers that have the wall, right? So an S-symmetric thing will get through one wall and act the same on the right and left on one module, and it will not act the same on the right and left on the other. Okay. But anyway, so this is a map of ZV inverse algebras that sends this guy to the class of that guy and is an injective homomorphism. I mean, eventually, I forgot a mo. There we go. Okay, so I was just trying to convince you that this is a homomorphism. With these claims, I showed it when at least m is always 2 or 3, or infinity, because you don't need anything when m is infinity. The fact that it's injective is some kind of upper triangularity, and we'll see that later or very soon. Yes, yes, absolutely. So whenever you have, so by the Grothendieck group, I mean the split Grothendieck group. So given an additive monoidal graded category C, then its Grothendieck group is, by definition, the ZVV inverse module generated by the class of objects for all objects modulo the relation that that the class of M shifted by 1 is V times the class of M, and that the class of M plus N is the class of M plus the class of N, and the ring structure is given by this. This is not a relation, but this is the ring structure. Now, when you have a Kroll-Schmidt category, okay, so you don't really want to take the Grothendieck group of an arbitrary category. I was actually just about to get to this, so this is a nice segue into the abstract stuff I was just about to do. You don't want to take the Grothendieck group of just an arbitrary additive category. Weird things can happen. Because in an additive category, it's not necessarily the case that something splits into indecomposable objects in a unique way. Right? Whereas if it does split into indecomposables in a unique way, then indecomposables form a basis for the Grothendieck group. You just take anything, split it into indecomposables, it becomes a sum of these things, and there's no way to split them in any other way, so there's no other relations. But if that's not the case, then you're in trouble. So what you're interested in is called a Kroll-Schmidt category, okay? Which is the kind of category that has that property. Okay, so I was going to have exercises on Kroll-Schmidt categories actually next week. I could move them earlier, but the point is that only Kroll-Schmidt categories are worth taking Grothendieck groups of. Okay, so what it means to be Kroll-Schmidt, it's the same. Well, yeah. So Kroll-Schmidt means that means unique decomposition into things that can't be split further, into indecomposables. But really, it's better to even go one step further and to only take Grothendieck groups of Cherubian categories. Actually, really, it's almost the same. I think Kroll-Schmidt implies Cherubian. I forget. So Cherubian is also sometimes called idempotent closed. Says that you include all summands. Right? For instance, here's vector spaces, and you can take the subcategory of vector spaces with even dimension. Okay? This is just a stupid subcategory because, I mean, this indecomposable is two-dimensional. It really should split into one-dimensional things. If you want to understand Hom spaces, it's as if it splits into two one-dimensional things. But you've sort of artificially said it's not splitting. It's not splitting. All right? That's just dumb. But there's an idempotent inside a 2 by 2 matrix, 1, 0 on the diagonal, which projects to one of these two summands. You might as well include the image of this thing. If you include the image of it, then you have the one-dimensional thing. Right? So to be Cherubian is to say that all idempotents have an image. Okay? I.e., all summands are also objects. So what does it mean to be a summand in an arbitrary category? That's what it means. It means that there's an idempotent that projects to you. So if all idempotents have an image, that's what it means to be Cherubian. And so if you're Cherubian, then under some very mild assumptions, like you're working over a local complete ring or something, then you're Kroll-Schmidt. So Cherubian plus work over a field or just any complete local ring. This is why people don't work with Z modules. Z is not a complete local ring, and all sorts of weird things screw up, and the Grothendieck group is weird. But if you work over a complete local ring, then life is easy. So there are some stupid algebraic technicalities, which if you've never seen them before, now at least you know why they're there. You should really only take Grothendieck groups of Caribbean categories over complete local rings. Yeah, I'm really looking inside categories. I'm looking inside finitely generated categories, basically. So the thing is that if you're an infinitely generated category, your Grothendieck group is 0. This is a weird thing, but the Grothendieck group of vector spaces is 0. The Grothendieck group of finite vector spaces is not 0. Okay? I don't know if you've ever seen this, but the infinite dimensional vector space, direct sum the one-dimensional vector space, is the infinite dimensional vector space. So subtracting something from both sides, you get that the one-dimensional vector space is 0. All right, so this is why Grothendieck groups don't even make sense unless you're in a reasonably finite category. They make sense, but they're boring. So yes. So in that case, we shouldn't be looking at Bot-Samelson bimodules. These things, BSBT, BSBT, whatever. Because you've already seen that they have interesting summands that aren't Bot-Samelson bimodules. Some weird things. So we should work with summands of Bot-Samelson bimodules. So the definition, a Zergel bimodule is a summand of a Bot-Samelson. Or, you know, maybe it's a direct sum of tensor products of grading shifts of summands of Bot-Samelson bimodules. So they form a category of Zergel bimodules, which is inside our bimodules. And it's Caribbean.
You're just taking the full subcategory.
Yes, the full subcategory, all morphisms. Okay? So this is the thing that we're allowed to take Grothendieck group. So Bot-Samelson bimodules are the things that you get to play with because they're easy to understand. A summand inside a Bot-Samelson is some crazy, terrible thing. I've only shown you the nice ones. Most of them are awful. Okay? Right? Just like, you know, you only see the nice cosmologically polynomials, but most of them are terrible. Okay? I mean, really, Zergel bimodules are very hard to study. Bot-Samelson bimodules are very easy to study. But for just algebraic reasons, you should be considering these. So the theorem. Yes, this is all Zergel. So, I mean, the name Bot-Samelson comes from Bot-Samelson resolutions. Right? There are these nice resolutions of Schubert varieties in geometry, and you know, you've kind of seen vaguely that this is related to global sections, like cohomology of something related to the phi variety. Well, this is the cohomology of the Bot-Samelson solution. Equivariant. So, here's the big theorem. It's called the Zergel categorification theorem. And this is going to include everything that really one needs to know about the structure of this categorification. So, there exists a unique, indecomposable summand, which I'll call BW, living inside the Bot-Samelson attached to a reduced expression. Okay? Well, there's actually many summands. So there's a unique indecomposable summand, which is not a summand of BSY for any shorter expression. Okay? So this is the sort of upper triangularity kind of statement, right? This guy is a whole bunch of summands, but only one of them is not something you already saw. Right, so for instance, as an example, we saw that BS, BTBS, when M is 3, was BS plus this new guy. Well, this is something we already saw. So this new guy would be, if he's indecomposable, which he is, would be the Zergel bimodule BW. Okay, well, you know that this depended on a reduced expression, but this does not. This is independent of reduced expression. So that's number 2. Well, let's just temporarily call this B underscore W. Temporarily, but number 2 says there exists canonical isomorphism B underscore W isomorphic to B underscore W prime when they're both reduced expressions for the same element. Okay, and because of this, we'll just write it as BW. Okay, so back to this computation, right? This new guy was what? It was this thing I was writing as BST, R tensor over big invariance, R. Okay, well, if we'd done this with a different reduced expression, okay, we have a different decomposition. This one has BS, that one has BT, but the highest term is still the same. So these two are actually canonically isomorphic. Right, so they really are, we can just think of them as being the same thing.
When you say D can decompose into some,
Yeah.
is that physically as a submodule?
Yes. Yeah, there's only one. Well, so because when something appears in multiplicity 1, it appears canonically. Yes.
So it's like an isotypical component.
Yes, exactly. So yeah, an isotypic component is canonical.
Yeah.
But this is an isotypic. But this is it has only multiplicity 1, so it itself is canonical. Yes. Okay. So we've listed a whole bunch of indecomposables, one for each element of W, but these are all of them. Okay. So these BWs with grading shifts form a complete list of non-isomorphic indecomposables. Okay? So these are all of them, and no 2 of them are isomorphic. It's clear that no 2 of the BWs are isomorphic almost by definition, but nothing's isomorphic to something with a grading shift either. And what this implies is that the Grothendieck group of Zergel bimodules has a basis given by the classes of these guys as a ZVV inverse basis.
So it's in the second thing, are we assuming that W bar and W bar prime are reduced expressions?
Yes, 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 yes. So this is only defined for a reduced expression. So non-reduced expressions are obviously interesting, but all of their summands will have already appeared. Okay, so part 4 is that, unsurprisingly now, the map from the Hecke algebra to the Grothendieck group of Zergel bimodules is an isomorphism. So this earlier theorem said that it's injective. The fact that it's surjective is also this upper triangularity as well. And part 5 has its own name. It's called the Zergel-Halm formula. This is something that I mentioned the other day, although in the context of category O. You take 2 Zergel bimodules, not necessarily indecomposable, just arbitrary. Okay? Then their Halm space between them is also an R bimodule. Right, R acts on each one of these things on the left, so clearly acts on the Halm space. And this is free as a right R module or as a left R module. In fact, because each of these individually are free as a right R module. So Halm should be free as a right R module. That's fairly clear. I've chosen right to be special. When I talk, it's always going to be right that I care about, but Left is just as good. And the graded rank, so if we choose a homogeneous basis of this as a right R module, then the graded rank is supposed to be the pairing between these things in the Hecke algebra. So this is the standard pairing from yesterday in the Hecke algebra.
Epsilon WA.
Exactly, epsilon of WAB. So, good. So we started a little late, so we have time to just do a couple examples. Are there any questions about the statement of the theorem?
Yes. Could you indicate, this may be a technical question. Could you indicate, you assumed your base field to be R?
Yeah, so from the beginning, I've decided my base field was R. And as I said, there's generalizations, but let's just use R.
Let's just use R.
Right. I mean, so this Zergel categorification theorem is going to be true over any complete local ring. Okay? It is, except that, you know, it needs to be a complete local ring for which the reflection representation is defined. Right? So when I define the reflection representation, there are these numbers, cosine of pi over m, right? These are real numbers. They are not rational numbers. Right? So you have to be working in a ring that's big enough to hold them. But so long as you're in a ring that's big enough to hold them and it's complete local, that's fine. You know that what is not in this theorem, what is not in this theorem is any statement about what this basis is. Okay? I said that this thing has a basis of the right size, but I did not say that it was the Kazdan-Lustig basis. That is going to depend on the ring that you're working over. It's going to depend on the characteristic. All right, so the big question is what basis of the Hecke algebra? Okay.
Okay, so is it that here, no matter what, okay, so you want the representation to be of some kind, but here the R does not play.
Yeah, R has not yet played a role.
Okay.
Could be complex numbers, could be anything. But it has to, you can't work over Z, because then taking the Grothendieck group doesn't make sense. But you should work over a complete local ring.
But if you're working on a finite field, what does the Cartan matrix mean? Or you just have to have something that works?
It just makes perfect sense. Why not?
With the cosine whatever.
Yeah, all right. So you just need something that has the same algebraic properties. So this is on the exercise sheet. Is how to understand what algebraic properties are important in the Cartan matrix, and how to define it over general rings. So yeah, the big question is what basis of the Hecke algebra it is, and that will also tell you how big the Hom spaces are. They're the same question, right? Because if you know what the classes of the indecomposables are, then you know how big the Hom spaces are between them. It's really the same question.
So why not just define your Kazdan-Lustig polynomial to be the image of BW?
Right.
And then work with it and throw away the old definition.
Yes. So the answer is, then you would have no idea what it is. I mean, it's certainly self-dual. That's something you can show, right? It's a product of HS's, and there's some self-duality, which there's a duality in this category. We haven't talked about it yet. It's self-dual, okay? It is upper triangular, okay? You know, it's going to be something, so BW will certainly be HW plus some sort of coefficients. I don't know, I'll call them H prime YW times HY. So it's self-dual. It has this form, but it need not satisfy H prime YW is in VZV. Okay. So this condition may not hold. Finite characteristic, it fails for some examples. So, you know, that means that this whole algorithm that we use to actually figure out what Kazdan-Lustig polynomials were won't work. Right? We just have no algorithm for figuring out what it is. So this is a perfectly good basis. So in characteristic P, this is called the P canonical basis, or the P Kazdan-Lustig basis. This is a wonderful basis. These need to be studied. This is going to be the focus of a lot of mathematics coming up. The big 21st century question, what are the p-canonical bases? But we don't have an algorithm to find them or anything useful. What's great about Categorification polynomials is that you can just find them and compute them.
So this basis depends on that's where the dependence on the base ring.
Yeah, it absolutely depends very strongly on the base ring.
Actually, one doesn't expect it to have positivity properties.
Well, it's guaranteed to have positivity properties.
Just
Because it's the Grothendieck group of something, right? You can only take direct sums. You can't take direct minuses. So it has positivity properties. It's a nice positive basis.
But it will not be a polynomial be necessary.
Yeah. I mean, yeah, it could have constant terms. It could have negative terms. It could be all over the place. So yeah, that's the big question: is what is this basis? That's the deal. Let me just do a couple examples. Yes. Yes. So R is only acting on the right. Yeah. So I'm about to do examples of this. Okay. I'll have you ask your question again in a second. So let's hum from R to R as an R bimodule. This is just R. Okay? Well, this categorifies 1. The pairing in the Hecke algebra of 1 and 1 is 1. Okay? So this is supposed to have graded rank 1 in degree 0. This is v to the 0. Okay? So that's exactly as desired. So hum from R to BS. Okay, so what is this? Right? Well, we've just said that CS is the unique thing for which left and right multiplication are the same. And if you have a map from R to BS, the image of 1 has to go to something for which right and left multiplication are the same. So this is going to be some multiple of CS. It's going to be actually some multiple of CS by R acting on the right. Okay, so it's actually going to be CS times some F for F and R. So this is an exercise. Check that these are the only possible maps. So in particular, this Hom space is a free R module generated by the map which sends 1 to CS. And this is a map of degree 1. Okay, so this is actually R shifted up by 1. Okay, well, the pairing of 1 and HS, okay, remember what that was. That was the coefficient of the identity in HS, and HS is, oh God, V plus HS. So we're looking at the coefficient of the identity here, which is V. Okay, so this is generated in degree 1, this is V. Okay, this is how this matches up. Okay. What happened to my sheet? There it is. There it's not. What happened? Ah, that's. So then hum from BS to BS. Okay, well, first let's see what the graded rank should be. HS paired with HS. Using a junction is 1 paired with HS squared. Yes?
Should I think of it as why don't I think of it as V inverse?
Yeah, it's just your choice. It's just a normalization, right? But yeah, the grading shift by -1 is the thing that puts the identity in degree +1. Yeah. I mean, it's the usual shift that m shifted by n in degree I is m in degree n plus I, right? And that is exactly the thing which behaves this way. So to continue this calculation, you know, this is HS squared. We already know that's V plus V inverse times HS. And we already computed that this is V, so we get 1 plus V squared. Okay, so this is supposed to be something, this is supposed to be R plus R shifted up by 2. Okay? And in fact, we already know what the Hom spaces are. We have the identity map. And we also can left multiply. Right, we're looking at this as a basis under right multiplication. We can left multiply. But left multiplying by something symmetric is already the same as right multiplying. But left multiplying by alpha s is something new. This is left multiply by alpha s. And so, again, it's not so hard to check that this is a basis. Okay? And so far, in fact, all the Hom spaces we've computed have been in positive degree only. Okay? I just want to do one more example to show you that that is clearly not going to always be the case. So Hom from BS to BS. Okay? Well, if you remember, BS is isomorphic to two copies of BS with shifts. Right, so there should be a projection map of degree +1 and a projection map of degree -1. So there should be a map of degree -1. Well, I mean, epsilon of hs cubed is this times v plus v inverse. So it's v inverse plus 2 times v plus b cubed. So this is the graded rank of this Hom space. And there's a map of negative degree. There's also a map of positive degree, but there's more maps of positive degree. In fact, so this splits into two copies of BS. So you have the degree of -1 map and the degree +1 map. And then you also have the endomorphisms of BS. And that accounts for the other two. All right. So that was a bunch of examples to give you an idea how you can actually use the Zergel Hom formula to check that a bunch of modules, a bunch of maps that you've defined are in fact a basis for Hom spaces, and so forth. And we're going to use it a million times in the future. I think I'll stop. Although I guess because of all the stops, I haven't given my full. Maybe I've given it now. But this is a good time to stop.